Now let's talk about a very important idea of isomorphism of graphs. So isomorphism is, I guess you can probably look up some etymology for why it's called that, but isomorphism is a word that is commonly used in math, and it basically means when things are the same as far as you care. So when two things are, different in some way that is not relevant to the mathematical structure of them, then they are isomorphic. So in this case, two graphs are isomorphic when they essentially have the same vertices and the same connections, despite possibly being drawn differently. So let's define this and let's do some examples. An isomorphism from a graph G1 to G2 is a bijection of the vertex sets. So it's a map from the vertices of G1 to the vertices of G2, which is a bijection, such that a pair of vertices in the first graph are connected by an edge just for clarity, an edge in E1, if and only if their partners in V2 are connected by an edge there. So this is basically a rigorous way of saying what we just said before. Two graphs are isomorphic if you can match up the vertices so that they are connected in exactly the same way. And in this case, so G1 and G2 are said to be isomorphic if there exists an isomorphism between them. So let's see some examples. I have drawn some graphs here, so let me try and copy them. First one is a nice bipartite graph. In fact, it is a complete bipartite graph. So all of the edges that you could draw, keeping it bipartite. I think that's all of them. So this is G1, and G2 will be, oh my gosh. G2 is this graph. Looking like this. So the question is, are these two graphs isomorphic? And the answer is yes. So the function that sends, so let me just write it like this. We're going to give an isomorphism sending vertices which we'll label by A's on the left-hand side and B's on the right-hand side. Also, just a quick note, I don't know if I've used this little footed arrow before, but it's just a way of distinguishing the arrow that means the map and the arrow that means the image of a particular element. All right, so let's label these vertices to describe what this isomorphism is. So if this is A1, A2, A3, A4, and A5, then we should label B1, B2, B3, B4, and B5. So the claim is that this map, which sends A sub I to B sub I in each case, is an isomorphism. So maybe let's not check every single case, but let's check a couple of vertices just to see if we know what we're talking about. So we're saying that A1 and A3, since they're connected in this graph, B1 and B3 should be connected in this graph. And they are. That checks out. In fact, let's just say A1 should be connected to A3, A4, and A5. And indeed, B1 is connected to B3, B4, B5. So that checks out. And similarly, maybe let's pick A4 is connected to A1 and A2. So B4 should be connected to B1 and B2. And it is. And if you check, all the possibilities, you will find that they always match up exactly. And that means that this map is an isomorphism. So maybe you can already see from this example, but certainly you can find more examples if you are not convinced yet, that you can have two graphs that look quite different the way they're drawn and still be isomorphic. So how do we tell if graphs are isomorphic or not? To show that some graphs are isomorphic, the most straightforward way is to write down an isomorphism between them. Which is not to say that it is easy, but it is certainly a thing that can be done. And it's a very clear way of showing that an isomorphism exists is to just exhibit one. But the other direction, how do you show two graphs are not isomorphic? So of course, it's not enough to write down some map and show that it's not an isomorphism, because to show they're not isomorphic means you have to show that no isomorphism exists. So every possible map is not an isomorphism. And of course, it's totally intractable to check every possible map, but fortunately, there is a much better way. So how to show the graphs are not isomorphic is to use an invariant. Which is to say, if something is preserved by isomorphisms, so that's what we mean by an invariant, something that is invariant under an isomorphism. So if you have something, some fact about your graph, that's preserved by an isomorphism and different for your two graphs, then they must not be isomorphic. Because, of course, if they were isomorphic, then since this thing, whatever you're considering, is preserved by the isomorphism, they would have to have the same thing. So that's being a little bit vague. What kind of things can serve as an invariant? Well, many things, and you can probably come up with your own, but just to give some ideas to start with, the number of vertices in your graph, so that's a very basic one, we saw in the definition that an isomorphism involves finding a bijection between the vertex sets of our two graphs. So if they have different number of vertices, we certainly cannot find a bijection. So in that case, you can conclude that no isomorphism exists. And along similar lines, the number of edges, if you have an isomorphism between two graphs, then it matches up each edge in one graph with an edge in the other graph. So if you have a different number of edges in your two graphs, then they cannot be isomorphic. But besides just, the raw material of the graph like this, there are many more, slightly more subtle things that you can look at, such as degrees of vertices. So for example, if one graph has a vertex of degree 5, and the other graph has no vertex of degree 5, then they can't be isomorphic, because under an isomorphism, a vertex of degree 5 would turn into another vertex of degree 5. So degrees of vertices, subgraphs. So for example, if you have a triangle as a subgraph in this one, but not in this one, again, that means they're not isomorphic. So let's see examples of some of these things. So let's draw a lot of graphs. So here is a graph with 5 vertices. Here is another graph with 5 vertices. It's a little bit of a messy drawing. Let me a little bit draw better. Oopsies. Okay. So these are two graphs, both with 5 vertices. But if we count the edges, if I've drawn them correctly, this guy has 1, 2, 3, 4, 5, 6, 7 edges. And this guy has 1, 2, 3, 4, 5, 6 edges. So they have a different number of edges. So not isomorphic. What about, so the same graph on the left-hand side, but let's say we add an edge to this graph. So it only had 6 edges. Well, here we go, huh? Now it has 7 edges. Now are they isomorphic? They have the same number of vertices, and they also have the same number of edges. So in order to test this, we should look a little bit deeper. And what's the next thing that we wrote down? The degree of vertices. So let's check the degrees of the vertices in these graphs. So in the left one, let's see, this vertex has degree 2, this vertex has degree 4, 2, and this has degree 3 and degree 3. And in the right-hand guy, these vertices each have degree 2, and these vertices each have degree 4. So we can see that they are different because, for example, this graph has a couple of vertices of degree 3, and this graph has none at all. Huh. I wrote some nonsense on my notes, but I think what I've said is true. Someone please correct me if I'm wrong. But, so for example, the first graph has a vertex of degree 3, second does not. So they are not isomorphic. What about, let's see, how is this example? Yeah, okay, this is a good example. So this graph and this graph. So what kind of things do we know to check so far? Well, they both have 5 vertices, so they're the same that way. They both have 6 edges. Since we counted this is the same as this graph, it has 6 edges. This is just this graph minus 1 edge, so it also has 6 edges. Let's quickly look at the degrees of the vertices. This has degrees 2, 3, 2, 2, 3. And this has degrees 2, 2, 2, 3, 3. So that doesn't turn up anything either. They have the same number of vertices of all the same degrees. 3 vertices of degree 2 and 2 vertices of degree 3. So they're starting to look quite similar. But the very last thing we noted up here is that, for example, we can look at subgraphs. This is a thing that will often be helpful. And you will remember that we had this fact earlier that a bipartite graph, of which this is an example, cannot contain a triangle as a subgraph. And you can see that this guy does contain a triangle as a subgraph. So there you go. That differentiates them. So first graph contains a triangle as a subgraph. The second does not. So they are not isomorphic. And, there's sort of an infinite variety of these kinds of techniques and the ways you can combine them. So another example to illustrate why these graphs are different is they have the same number of vertices of the same degrees. But if you look at the relationships between those vertices, for example, on the left-hand side, the 2 vertices of degree 3 have an edge between them. And on the right-hand side, the 2 vertices of degree 3 do not have an edge between them. So that's another way that you could differentiate these graphs. So it really, it really is something that you can use use whatever comes to you. Feel free to experiment and find your own ways. So another thing we can do along these same lines is start talking about symmetry. So thinking about isomorphisms in this rigorous way gives us a rigorous way of talking about symmetry. So a symmetry of a graph is an isomorphism with itself. So now we're not talking about whether an isomorphism exists. An isomorphism of a graph with itself certainly exists. But now we're talking about being able to quantify and sort of work concretely with all of the different symmetries of a graph. So, for example, if we have a graph with 2 vertices like this is the complete graph on 2 vertices. This thing has 2 symmetries. So there is the identity, which there always is. A goes to A and B goes to B. And there is the flip. A goes to B and B goes to A. So there is a symmetry that sort of does nothing, and then there's a symmetry that flips the two vertices. Let's look at another example. This graph so let me label these vertices again, A, B, C, D. This graph has 4 symmetries. Again, the identity. So for brevity, I'm just going to write the letters in the list of where they go. So this means A is going to A, B is going to B, C is going to C, and D is going to D. There is the symmetry where we flip along this line of symmetry. So that is flipping A and C. Or yeah, let me not write these at all. I think that might not be illuminating at all. Let's just describe all the different symmetries. We can do nothing. That's the identity. We can flip A and C, which is flipping along this line of symmetry. We can flip B and D, which is flipping across this line of symmetry. And we can flip A with C and B with D, which actually amounts to just a 180-degree rotation. And these are all of the 4 symmetries of this graph. So basically, thinking about isomorphisms and thinking about symmetry in this way allows you to quantify how symmetric something is and allows you to start working with symmetry in a mathematical context, which is extremely useful, especially for doing things like abstract algebra, but in many fields as well. So here is a little problem that I want to leave you with. This triangle has 6 symmetries, which are rotations. So you can rotate by 1/3 of a turn or rotate by 2/3 of a turn. And flips. So you can flip across this line of symmetry, or this line of symmetry, or this line of symmetry. And I guess that's 5 things I said before already, but there's also the do nothing, the identity. That's 6. So a surprisingly hard exercise. Or at least I found it so. You may have a different experience. Can you write down a graph with exactly 3 symmetries? So this is hard because, at least for me, when I try to write down a graph with 3 symmetries, it turns out that I have drawn a graph with 6 symmetries. So it's quite hard to find a way to break those extra symmetries and get it down to exactly 3. This is quite a fun thing to play with, and hopefully will give you some practice with thinking about isomorphisms and thinking about symmetries.